Great, thank you, Brian, and thanks for showing up for a night on systems. And the topic that I'm going to give a very quick talk on is systems performance. This is also something that I have a book that's being published this year by Prentice Hall. My name goes on the cover, but there have been many contributions by engineers. In fact, many engineers in this room have contributed to the book. And it's something we all feel strongly about, and that is making sure that our systems go very fast. So what do we mean by the system? I've got this diagram that shows what I'd call a partial stack. And this goes from applications down to metal. What I'm not showing is you also have your clients and the front end, and those are what you'll use for distributed systems or when I'm accessing it from a browser. I'm focusing here on the actual system, the back-end systems that are running your databases, your applications, your web servers. And systems performance is the analysis of everything. So you can think of it as thinking LAMP and not AMP, LAMP with a capital L, because we want to spend a lot of the time inside the operating system. This is an activity for everyone, so from casual to full-time. I get to do systems performance as a day job, which is really exciting, but for most of us, it's just a small part of what you do. And for many people, you're doing database performance, you're doing application performance, and you may start with a quick check of operating system health, looking for bottlenecks, looking for that low-hanging fruit that can give big wins. And also, it is the analysis of the application as well. So this isn't just about looking inside the kernel, which I've drawn here, and all the internal components. It's also about discovering problems with your application and the way it uses the system. Some people skip systems performance altogether, even though it's really exciting and leads to many big wins, because they are the application developers and they know that there's big fish to fry inside the applications. Now, if you ask me, I'm a customer, I have a performance issue, where is it? My instinct is to say, oh, it's the kernel. The kernel is, I know all this trash that's inside the kernel, trash that I've been exposed to all the time, and all these bugs that I've spent so much of my life working on. Surely the problem is the kernel. The applications, the customer applications, they must be perfect. I haven't been inside them, I bet they're immaculate, but the kernel, which I spend my time in, that's surely the problem. And the funny thing is, when I talk to application developers, they have the opposite instinct. They say, surely the kernel's perfect, surely the kernel's immaculate. There'll be no problems inside the kernel. It's my own application code that's really trashy, that's where I'm finding the bugs. So reality is somewhere in between. All software can have performance issues, the target is everything. By doing it from the system, you do have a different perspective, and sometimes you can identify your application performance issues more quickly. However, there's also a load of application-based performance analysis as well. So people specialize in MySQL performance analysis, and MongoDB, or Erlang, or Java. They are coming at it from the top of the stack of the applications, and for systems performance, we're often coming from the bottom, from the kernel. So we can solve different classes of issues that may be missed otherwise. Some background, sorry, it's a bit faint. 1990 systems performance, proprietary Unix, closed source, and static tools, and typified by tools like VMstat, which was written a very long time ago, originally written by Bill Jai a very long time ago for BSD. And you have limited metrics and documentation. Some performance issues just could not be solved. And I'll go into that a little bit more, which was accepted because we didn't know a better way. The vendor gave us various tools. That's what you use for performance analysis. If you couldn't solve it, that's life, and you could file a ticket with the vendor. Some performance experts got good at inference and experimentation. And I was doing consulting at the time for performance, and I got really good at this. I have a bit of a background in physics when I went to university, and I found that things like the scientific method were really useful for systems performance analysis. So all that time I spent at a lab bench with doing optics experiments with prisms and the double slit experiment and Michelson-Morley, that taught me to take a black box and then go through this painstaking methodology to infer its internal behavior. And that's great, that's what we did. There was a lot of literature written about systems performance at the time about how you would do that. But nowadays, open source kernels are the norm. There were open source kernels back then. So treating the kernel as a black box that I need to perform these experiments, I could just read the source code. All of that expertise I had, which was very good when I was doing performance consulting. It's now no longer a big edge because people can just read the source code. You don't need to go through all these experiments to figure things out. So the source code gives you the ultimate documentation. We have dynamic tracing, which I want to mention very briefly, so that you can observe everything inside that stack. Visualizations to comprehend many metrics. We're now exposed to a lot more. Cloud computing makes a big difference, and I mentioned that a little bit of that here. So in our stack, we don't talk to Metal directly. We do have a layer of resource controls often in the picture. And like I said, with the original systems performance, the literature is still around. And so when you're learning systems performance, it often fails to guide you through checking the cloud-imposed limits because the cloud didn't exist back then, or resource controls didn't exist back then. But in fact, if you are deploying in the cloud, it's often those resource controls that are the first things you hit before you hit Metal, because they're imposed to prevent noisy neighbors so that you use your share of the system. So it's really important that we now pay attention to this. It's a big part of systems performance. And we can also do methodologies more than we ever have before. So just to give you an idea of things that have changed, in the 1990s, operating system internals, you'd read textbooks, and there's some fantastic, these are some of my favorite textbooks on kernel internals, and you'd have this mental diagram, a working understanding of how the system, how the kernel operated. Nowadays, we have DTrace. This is a picture of the DTrace pony. I can study the source code, and I can observe in production everything with dynamic tracing. So all of that stuff, I can create a DTrace script, bring up nanosecond timestamps, test hypotheses very quickly, and actually see it. Another way to understand how things have changed, in the 1990s, I did a lot of work with Solaris, and so this is a picture of, this is the same operating system stack. I've added some hardware. This is Solaris 9, and the observability that we really had in Solaris 9. Now, Solaris 9 was closed source. At the time, Solaris 9, one of the main features was performance. So Solaris 9 was, it had resource controls. Sun Microsystems had a very large performance team of over 100 people, and it was considered to be a very observable and high-performant operating system. Even though, once you went below the system call interface, things got pretty dark. And working on performance issues down here by the customer, really, really difficult to do, really prohibitive in terms of time and cost to go through the arduous experimentation process and to figure things out. But we didn't know better. We thought that was great because that's what the vendor gave us. Nowadays, we have DTrace. So this really turns on the light for all of these layers. And when we want to analyze performance down to Metal, we can. I've given these, I've talked about DTrace a lot, I've done a lot of work with it. And it's one thing to say, yes, DTrace can light up all of these areas. It's another to show how. And so I've been busy decorating this diagram with some of the DTrace scripts that I use to analyze different layers. And so this has some of my favorite scripts, like ones I've been using recently. I've got my TCP retrans snoop, so I can go into TCP and I can trace just the kernel function that's doing TCP retransmits, instead of doing, say, TCP dump, which is CPU expensive because I'm tracing every packet. I've got TCP time wait because I had performance issues there, and I wanted to be able to analyze the kernel state and the kernel context to understand how those sessions were operating. So this is what modern performance looks like. It doesn't have to be DTrace. It does have to be dynamic tracing so that you can see, you can answer any question you feel like. Static tracing does solve a large number of this. This diagram does encompass a lot of scripts. To briefly just expose you a little bit, there's going to be some talks later that go into DTrace in more detail. If you've never seen, hands up if you have used DTrace. It's a better question. Wow, I have like 70% of people here have actually used DTrace. So this is why I'll go through this very quickly. If you haven't seen it before, it does let you do things like this. So this is, let's say I was working on a performance issue in ZFS sparse sync, which is flushing transaction groups. I can open up the kernel source code, which is amazing that we can, because I used to do this pre-open source. I can open up the kernel source code, look at a function, and as a one-liner say, let's just time it, and print out when that was called, and then the duration of that kernel function. This is entirely safe. I don't have to worry about running this in production. The overhead is being minimized because of the architecture of DTrace. And this is why it shines a light into all those dark areas of the kernel, and I can start answering arbitrary questions. Now, a lot of people love Linux, and I just wanted to mention Linux as well. There are 2 DTrace ports in progress. There's the DTrace for Linux by Paul Fox, a UK programmer, and Oracle has its own one as well. There's also SystemTap, which I've used a lot, and SystemTap does dynamic tracing, and was created at a time when there weren't the DTrace ports for Linux, but for a similar role. So being able to do programmatic, low overhead, dynamic tracing inside the kernel, and later in user land. I've used SystemTap a lot. Actually, I was wondering if I could give it my talk. A lot of what's on the wall is some performance visualizations I've been doing in the system. And there's actually quite a lot of this stuff. Some of this is DTrace and some of this is SystemTap. So it was from a particular issue I was working on, if you want to browse that later to see what it looks like. So just as an example of dynamic tracing in Linux, however, I could do DTrace and I could do SystemTap. Perf has dynamic tracing, and perf is rapidly being considered the core performance tool while the DTrace ports are incomplete. And with perf, you can actually say, perf probe add TCP send message, I want to trace that guy, and then quickly show stack back traces with the userland process of who is calling that. So this is not using a static probe, it's not using some pre-baked, cooked-in infrastructure or observability. I'm just picking a kernel function and saying, show me some information. This is a little bit, this doesn't do everything that DTrace does do, which is why we still need the DTrace ports to be completed. And so perf happens to be a trace dump, analyze, old style kernel tracer. So you can't really do it in real time. It is CPU expensive because there's things you can't aggregate in the kernel. But if it solves problems, I will use it. Some other things I wanted to mention. DTrace is a very big, DTrace and dynamic tracing is a very big change for systems performance. But a couple of other ones quickly. Performance visualizations. In the 1990s, performance was often text-based, and some time series line graphs like this. I've got disk IOPS and I've got an old screenshot of Xload. And these days, we now have so much information. It's not just the ability, say, to instrument the entire stack, but also to get a rich amount of detail. So this is the full distribution of latency, and it's being plotted as a latency heat map. But there's plenty of different things we can do. This flame graphs are decorated on the wall, which is showing where the kernel is spending its CPU time. What else do I have? These are also distributions of latency that are measured using DTrace from different areas of the stack when I was investigating multimodality. So a richness of not just observability targets, but the information. This is really useful for us because there are many cases where you have multiple modes of latency and also latency outliers, and those influence the mean, such that the mean is more difficult to comprehend. I mentioned this earlier, cloud computing has made a big change in systems performance because when you're deploying on the cloud, it's not just the hardware resources you're running into, it's the cloud imposed limits. And so as part of a standard systems performance procedure, you need to check those as well. And as I mentioned earlier, there's a lot of literature out there for systems performance that hasn't been updated since the cloud. And so it's very common for people to miss out because they're basing their analysis on something a bit old. Performance methodologies is the last thing that has really changed. Back when we were closed source and we didn't have dynamic tracing, there were two real common methodologies for looking at systems performance. One I'd call the tools method, where for every vendor tool, I look at its useful metrics and then see if they identify problems. So I'm starting with the tools because that's what the vendor gave me. And the other one was coming up with ad hoc checklists, which were very useful as well. Now that we can do dynamic tracing of everything, we've got source code for analysis, we can really go to town and solve a lot of performance issues we couldn't before. And I've been doing a lot of this recently. So the use method, thread state analysis method, drill down, documenting drill down analysis and latency analysis in ways we couldn't before. Because without source code access and without dynamic tracing, doing a lot of methodologies is kind of an academic exercise. It's big T's. Wouldn't it be fun if we could get into the kernel and answer these? But we needed the tools and we needed the source code to really entertain these sort of methodologies. So that's my very brief talk. It's the new systems performance. We can really understand how systems work and new observability visualizations and methodologies. I and many other contributors have finished a book on it. We're really happy to get it published and to get it into your hands. And it is a great time to be working with systems, both enterprise and the cloud, for all the new problems and new observability methodologies we can explore. So, thank you. Any questions? Yes, go ahead.
For those of us in a SmartOS zone, many of those areas remain dark.
Right.
What does the future hold for things like TCP retransmits, etc.?
There are no hard questions. I'm sorry.
Okay.
There's an understanding here.
Yeah.
So
softballs.
I mentioned that it was important. If you're in the cloud, you have to understand when you're approaching your limit and when you're not. And for cloud environments, I may be a vendor, so Joint runs a cloud, AWS is a cloud, etc. You may not have permission to look inside the kernel because you can see other tenants. So what needs to happen is either the vendor exposes sanitized versions of the metrics for you, or the vendor gives you an API, basically a backdoor so that you can answer them. And at Joint, we do believe in transparency. We do believe in letting you can actually log into a smart machine and run IStat and MPStat and look at the physical CPUs, and from them understand, do your own diagnosis if you have a noisy neighbor, rather than assuming it and being in the dark until you file a support ticket. So people like you, it's up to the vendor. We have to give you, a means.
You people.
We have to give you a means to. So if you have a need, I do want to see TCP retransmits. I love it. We as the vendor need to give you the means to get that.
And we've done that for some. I mean, I think the challenge is that you are allowing people to instrument a kernel that is multi-tenant. And we've done that for some subsystems, and I think networking is the one that you're almost assuredly referring to.
And in fact, TCP retransmits.
In fact.
They're great. I love tracing that.
That exact thing is a current problem we have in production.
Yeah, and I think we need to take the same approach, which is to forsake our principles, which is what we did, and get filthy. We got FDs. Right, we did FDs because we what is the past for SOC? For what? If I forsake, whatever. Forsook. Anyway, whatever. Because we were willing to kind of do some filthy implementation, and we need to do that for the network as well.
Yeah.
No question. But we should expose the API. We do expose the API.
Yeah. So we can do the implementation and give customers. You have a legitimate need, and we have this amazing observability tool. We should give you a means to access it. But the fallback position is, if we never do, we can use it. And so you still benefit from it existing because we should be using it for support tickets and so on. If not, you can use it directly. Other quick questions?
Only softballs?
No.
Total softball.
Nice.
A couple slides back, you had the, I think you call it a flame graph, that one. Yeah.
That's a heat map. Flame graphs look like that.
Okay.
Yes, heat map. Latency heat map. Time, latency.
Can you, do you know of a good library that will make those things from data that I provide?
It's like question number one. We're in this world where it's like bystander syndrome. Everyone's waiting for someone else to write the library so that they can then put it in their
Mike Little Cooper? Mine.
Which one?
The one that generates those heat maps.
Yours?
All right, we should do that.
We should.
Yeah, we should do that.
I mean, everything under the sun will generate those nice little line graphs that you pasted up in the 90s,
maps, I mean,
right?
for whatever it's worth, but they're really easy to do. I mean, it's not that hard, but I'm happy to. I mean, we should.
So Brian wrote the code for that, and if Brian says we should just open source it.
Yeah, why not?
So like one weekend. Thank you for solving.
I mean, you're eating your pizza. Why not take a right?
Yes. So I did. One weekend I was bored and spent 3 hours running a Perl program that takes a latency trace dump and then spits out an interactive speak, just for times when I actually had a latency trace dump from whatever tool, and I needed to get to there. So if you go into github.com/BrandonGregg, you'll see I've got an implementation, a simple implementation, but Brian's is much fancier and sophisticated, so if we get that open source, that'd be really cool.
Yeah, we should.
I saw another question. Yes?
Is DTrace performant enough to just keep it running and maybe do preemptive alerts or have some kind of like pathology definition?
So can DTrace run all the time? Now I understand hesitation because I certainly wouldn't want to run TCP dump all the time or strace all the time on an application. Those strace in particular is hugely violent and will destroy performance. TCP dump can start to add up the cycles, and I know Linux does ring buffers to minimize the performance there. DTrace has a whole host of means to have the, and Brian obviously created most of them, to minimize the performance overhead. And just as a case in point, when we created a ZFS storage appliance previously, we put latency heat maps as a core observability feature, and customers would turn this on, and it would be on 24/7 by 365 at 1 second granularity, DTrace based. And this was a Sun, and now it's an Oracle major supported storage appliance. So yes, DTrace is running all the time. Overhead is only a problem when you want to trace a ton of events. Like, I do hesitate if I want to trace a 10 gig send receive, because you can get to over 1 million packets a second. And I'm trying to see if there's a different way to get there. Because even though the overhead is tiny, by law of iteration, it will add up. But another way to answer your question is, DTrace is fantastic, even if you do pay a little bit of overhead as an intermediate step before you can deploy baked-in statistics. And so some people may say, oh, I have this really urgent need, I need to have this for my application, major performance fires, I know I'm going to pay a little bit of overhead. And so with DTrace, I don't even have to stop and start the application. I can start detracing it immediately and getting this data. And then sometime later in my release cycle, actually build the baked-in statistics, which will have a little bit less overhead. So it's great for prototyping as well. But it does work for 24/7.
And your event counts need to be very, very high before you, I mean, if you've got probes firing 1 million times a second, 2 million times a second, that's going to be an issue. It's hard to have code for which that's the case. That's not either in the operating system kernel, or you've got a probe that's in the hottest possible loop. So I mean, if you, the cost of DTrace is proportional to the question. And if you ask questions like this that are very coarse, then the cost tends to be very, very low.
Great. One last question. Yes.
Your slide with all the scripts on it?
Yes.
Those in a library somewhere publicly available, or you keep those in your desk?
Some of these in the DTrace tool, I mean, I publish everything, because if I don't publish it, I lose it, and then I have to rewrite it, which has happened so many times. It's not funny.
It's actually hilarious when he rewrites something and
it's
he's
like,
lost. But
I spend like 10 minutes trying to find it. It's like, I know I've written this, why am I going to rewrite it? So everything is like, there's the DTrace toolkit, the DTrace book, and all the scripts in the DTrace book are on dtracebook.com. And I've got another tool. I've been recently thinking about how to collect these and share them more sensibly on GitHub. So I need to get that done. But everything I write basically gets public, so you can find it.
And the DTrace toolkit, which is on your Mac actually, has got a big, it's got a ton of these on the DTrace toolkit.
Yeah, things like OpenSnoop, StackSnoop, like a lot of these are already on Mac OS X, and so you can just do sudo OpenSnoop and play with that.
Indeed, it was one of Brennan's scripts that we used to, people would ask the question of like, well, if I'm running this as root, can someone see what's going on in the box? And I would run his SSH snoop, or do you have that?
I don't have it on there.
I've
run out of white space.
You run SSH snoop and you would just watch all SSH activity that's happening on the system. It's like, yeah, exactly, you can see everything. So.
Cool, well, thank you very much, and I'll turn it back to Brian.